In the smartphone market, there are two dominant operating systems. One is closed source, that's the iPhone, and one is open source, that's Android. The market for self-driving cars could play out the same way, with a company like Tesla becoming the closed source iPhone of cars, and a company like Comma.ai developing the open source Android of self-driving cars. George Hotz is the CEO of Comma.ai. Comma makes hardware devices that allow users with normal cars to be augmented with advanced cruise control and lane assist features. This means that you can take your own car, for example a Toyota Prius, and outfit that car to have something similar to the Tesla Autopilot. Comma's hardware devices cost under $1,000 to order online. George joins the show to explain how the Comma hardware and software stack works in detail, from the low-level interface with a car's CAN bus to the high-level machine learning infrastructure. Users who purchase the Comma.ai hardware drive around with a camera facing the front of their windshield. This video is used to orient the state of the car in space. The video from that camera also gets saved and uploaded to Comma's servers. Comma can use this video, together with labeled events from the user's driving experience, to crowdsource their model for self-driving. For example, if a user is driving down a long stretch of highway and they turn on the Comma.ai driving assistant, the car will start driving itself and the video capture will begin. If the car begins to swerve into another lane, the user will take over for the car and the Comma system will disengage. And this disengagement event gets labeled as such. And then when that data makes it back to Comma servers, Comma can use that data to update their models. So they can cross the disengagement event when the autopilot stopped working with the point in time in that video. So it's a nice labeled data feedback loop where you have video and the sections of video where the car system didn't work properly labeled for you. And from there, you can build quite a good supervised learning system. And that's really what this whole show is about an engineering problem that George sees as solvable but very difficult. It's a supervised learning problem. There's not really anything that is impossible to solve within it, and George is very good at explaining these complex engineering topics end to end, and he's also quite entertaining, and he's open to discussing the technology as well as other competitors in the autonomous car space. And this is great because I have unfortunately not been able to do very many shows about autonomous cars. We've done one with Frank Chen from Andreessen Horowitz and one with Lex Friedman, who has worked as a self-driving car engineer and teaches classes about self-driving cars. But other than those two shows, which were both high level because I just didn't ask very low level questions, we really haven't done a lot of material about this, and I would love to do more. So if you know of any self-driving car engineers or you are one, then please send me an email. Before we get started, I want to mention that we are hiring a creative operations lead. If you are an excellent communicator, please check out our job posting for creative operations at softwareengineeringdaily.com/jobs. This is a great job for someone who just graduated a coding bootcamp or someone who has a background in the arts who's making their way into technology. If you want to be creative and you want to learn more about engineering, check it out at softwareengineeringdaily.com/jobs. Cloud computing can get expensive. If you're spending too much money on your cloud infrastructure, check out Do It International. Do It International helps startups optimize the costs of their workloads across Google Cloud and AWS so that the startups can spend more time building their new software and less time reducing their cost. Do It International helps clients optimize their costs. And if your cloud bill is over $10,000 per month, you can get a free cost optimization assessment by going to doit-intl.com/sedaily. That's doit-intl.com/sedaily. This assessment will show you how you can save money on your cloud. And Do It International is offering it to our listeners for free. They normally charge $5,000 for this assessment, but Do It International is offering it free to listeners of the show with more than $10,000 in monthly spend. And if you don't know whether or not you're spending $10,000, if your company is that big, there's a good chance you're spending $10,000. So maybe go ask somebody else in the finance department. Do It International is a company that's made up of experts in cloud engineering and optimization. They can help you run your infrastructure more efficiently by helping you use commitments, spot instances, right sizing, and unique purchasing techniques. This to me sounds extremely domain specific, so it makes sense to me from that perspective to hire a team of people who can help you figure out how to implement these techniques. Do It International can help you write more efficient code. They can help you build more efficient infrastructure. They also have their own custom software that they've written, which is a complete cost optimization platform for Google Cloud, and that's available at reoptimize.io as a free service if you want to check out what Do It International is capable of building. Do It International are experts in cloud cost optimization, and if you're spending more than $10,000, you can get a free assessment by going to doit-intl.com/sedaily and see how much money you can save on your cloud deployment. George Hotz, you are the founder of Comma.ai. Welcome to Software Engineering Daily.
Hi.
I have been watching some of your interviews for a couple of years now. You're trying to build an open source self-driving car, and I like how open you are in discussing self-driving technology because it's actually been hard to get interviews with people who can talk about self-driving or who are willing to talk about self-driving. And I think it fits with your thesis because your thesis is that self-driving cars are going to play out like the smartphone market. The argument is that you can be the Android version of a car, whereas some of these other companies, or perhaps namely Tesla, will be the iPhone of the self-driving cars. So there are some ways in which cars are different than phones. We may have fleets of cars instead of people owning their own, but there are other ways in which cars are obviously very similar to phones, and cars are becoming more and more like smartphones. What are the strongest arguments for and against the car market playing out like the smartphone market?
So do we not have fleets of smartphones? We have the AT&T fleet, we have the Verizon fleet, different things operate on them. It seems pretty much the same to me.
Indeed. Do you have any theses about why it might be different?
So I don't really speculate much on like the far off future. I only say this because this is how the only industry that I can really make a comparison to has played out. I don't think much like 5 years in advance. I think it's usually a waste of time.
Got it. So what's the open source community like today for Comma? And when you interact with the people, what are their beliefs about the open source nature of self-driving?
Well, again, I mean, it's not about who cares really what happens in the long term. So first off, coming back to why not many people will talk about this stuff. The reason not many people will talk about this stuff is because they don't have anything, right? A lot of these companies are embarrassed by how little what they have actually works. It's extremely difficult to build these systems to make them actually work. As you know, you've seen even Tesla with high-class software talent, right? Like Tesla hires good software engineers. Who's GM hiring? They're having trouble. They're having trouble replicating like Mobileye.
How do you find out about that? Like, are there back alley conversations? Is there some secret forum where you gain intel about what's going on at GM, for example?
Well, you can watch the cruise cars drive. But in general, I mean, I've seen this paradigm over and over and over again. With a few notable exceptions like Apple, the more secretive people are, the less they have, right? There is no secret stealth startup. I can't think of one in history. Like, can you think of a startup in history which has been like super secret in stealth mode and then they launch something and it well exceeded expectations?
I cannot.
Neither can I. Remember, Apple's a company with a long, long history. Apple started out very similar to us.
So what do you think about their self-driving? I mean, do you have any intel on that, or could they potentially be in a good place?
I mean, the only intel I really have is you can read the lawsuit against that guy who leaked Apple's secret information. No, I mean, they have TPUs. It was interesting that you know that from the lawsuit. But no, there's no reason Apple would be particularly good at self-driving cars.
TPUs, so Apple has tensor processing units? The ones from Google or some different version?
Apple has a different version, right? So Apple's probably shipping the only real machine learning ASIC in quantity today, right? The Tensor Core in the iPhone.
Interesting. So what is working and what is not working, like industry-wide? Because it sounds like there's a lot of consistencies across the industry, the way you're depicting it at least. So what's working and what's not?
Well, so we have one example of level 4 self-driving cars, and that's humans. I almost don't even like the term self-driving car because it implies that the car drives. I think what we're really trying to build is a computerized driver. And then you don't think of yourself as building a car, you think of yourself as building a human, right? I mean, I think everybody gets this wrong. You're not trying to replace a car, you're trying to replace the human inside the car. So I suspect that your thing would look a lot more like a human than a car. So you have a lot of people taking this sort of DARPA urban challenge legacy approach. So everything in self-driving, at least like Zoox, Cruise, Waymo, they all even come from the same code base. It's open source. A lot of people don't know about this. You can actually read the Stanford DARPA urban challenge code. And all three of maybe the self-driving car companies that can actually drive have based off that code. Now, does this approach work? Well, the approach is this. They use LiDARs to very precisely map the world, relocalize themselves in the map, and then once they know exactly where they are, they know where to drive. They draw, you can draw the exact center line of the road, and then they just follow that line. You do a few clever things. If there's a car in the way, you might want to go around it. But for the most part, they're fancy line following robots. Now, this is very much not how humans drive cars. You have maybe us and Tesla in a camp trying to drive cars like humans drive cars, with cameras, with reactive, without precise maps, all that kind of stuff.
And so what's not working?
Nothing. I mean, everything we're doing is working. It just takes forever to do anything. Things just take a long time. We're finally getting to the point now where a lot of it is infrastructure. A lot of making this stuff work is infrastructure. We're taking in, I think we took in 350,000 miles of data from our Eons last month. Now, okay, let's process that and add that to our model.
So I'm very familiar with the software development process of something like accounting software, right? You build your first version of the accounting software, and then you give it to users, and the users tell you what works and what doesn't work, and you iterate on features, and then you can look at your monitoring and be like, okay, this server went down, we need to fix this back-end issue. I'm less familiar with the iterative process of a product that's mostly based on the quality of the machine learning models. Can you give me a description for the workflow and how you are benchmarking yourself as improving over that build, measure, learn cycle?
Sure. So the main metric we track is called disengagements. A disengagement is when the human had to take control back of the car. Now, you can divide disengagements roughly into two categories. There are planned disengagements, which is the human took control to, say, for example, get off an exit or make a lane change. And then there are unplanned disengagements where, the car drove the wrong way and the human needed to correct the car, or the car wasn't braking quickly enough and the human didn't feel safe, so they stepped on the brakes. Those are unplanned disengagements. So we want to drive unplanned disengagements to zero. So every month, we get all the data back from our cars about how they drove. Everybody uploads them. We don't get all of it back. We get about 70% back. 30% gets lost in the ether. But of what we do get back, we can measure how many disengagements there were, and we try to make that number go down every month.
What observations have you been able to make about what causes people to disengage?
Well, so one of the limitations right now, and this is a limitation of our model, we only have about a 40-degree field of view. So if a car cuts in very closely, if a car cuts in right in front of you, it doesn't see the car in time and the human has to step on the brake. So, this is one of these, okay, we need to.
And I'm sorry, I said the person disengages. I should have said the car disengages.
Well, no, it's actually the person who disengages. Sometimes the car will disengage, but almost all of the disengagements are user-triggered disengagements.
Oh, sorry. Okay, so disengagement means the human is interceding in the self-driving program.
Yes, it means I should have defined it. When the self-driving system is engaged, it means that the driving system is controlling the car right now. The human's paying attention at all times, but the software is turning the steering wheel, pressing the gas, pressing the brakes. A disengagement is when the human overrides the system, when the human steps on either the gas pedal or the brake pedal or turns the steering wheel.
Okay.
So yeah, this is the main metric that we want to drive to zero, or as close as we can get to zero. It's never going to be perfect, and it doesn't have to be. It just needs to be better than humans. But yeah, so we figure out what mistakes the cars are making. Some of them are happening because of quality issues, like the machine learning. Okay, that was just a difficult scenario. Then we add that to a special test set that we have to make sure to try to get future models to work in that scenario. But there's all sorts of subtlety there. And then some of them are just caused because, that car cut in really close and it wasn't available in the field of view of what we're currently looking at in the camera. So that's a feature that we're going to have to add.
When you look at something like that case, I think there was a Tesla accident recently where the car just completely swerved into a divider and crashed and killed the driver. that was something that was pretty concerning because as far as I know, the car was just following the machine learning model, the autopilot rules, and it just slammed into a wall and killed the driver. How do you discover the disengagement scenarios that are like more dangerous, or like how do you benchmark the safety level when you have these kinds of, I assume that was some sort of tail scenario that was really hard to identify during all the training. I mean, do you have any color on that experience?
It wasn't. So if you're talking about the Sunnyvale crash, where it hit the divider, that was the compacted divider. So the main problem there was not that the car swerved into the divider. This is a misnomer about what happened. It's that the car slowly drifted out of the lane. The driver wasn't paying attention, and then it crashed into the divider. If the driver was paying attention, they would have had plenty of time to correct the system, which is really important to communicate and make sure everybody knows that these are level 2 systems. And everybody knows that. But, even sometimes when humans are driving, they don't pay attention. So it had a lot more to do with the lapse of the attention of the driver than anything about the system. You can't expect these systems to be perfect. Maybe someday you can, but none of the systems today are. Even Waymo, who's probably the furthest along, still has, except for a few PR stunts, attentive drivers in all their vehicles. The Uber crash was the same thing. The car made a mistake, but the person was watching a television show.
First of all, I agree with you that there will be some open source solution to self-driving. When there are car accidents or fatal accidents with a open source self-driving system, how do you think the optics and the public response will differ from these closed source systems where there's a little more opacity?
I don't really think much about stuff like that. I'm an engineer. As far as public relations go, I think my basic assumption is that people aren't stupid and, just tell the truth and make it as open as possible. How it plays out, that's on other people. It's not on me. I don't spend a lot of time thinking about that.
Okay, fair enough. So let's get into the engineering then. So you have a set of devices that are able to outfit a non-self-driving car, a traditional car, with self-driving capabilities. Can you describe the hardware and software that is used to outfit one of these cars as a self-driving car?
Sure. So, the term self-driving car is kind of a loaded term. Really, what we're adding is it's driver assistance features. The two common ones are adaptive cruise control, which is what controls the gas and the brake, and then lane keeping assist, which is what controls the steering. So, as far as what we actually add to the car, we sell a device, no software on it. We just sell the device with dashcam software. But it's basically a smartphone in a case. Now, smartphone is almost everything you need to drive a car because smartphones look a lot like people. Smartphones have eyes, and smartphones have ears, and smartphones have different ways to communicate. And so there's software which runs on that phone that uses the camera to watch the road and say, okay, this is the trajectory that I need to send the car along. This is the object that's in front of me that I need to make sure I maintain a safe distance from. And then we interface with the car using another device we make called the Panda. It's just basically a USB to CAN bus bridge. Then we send signals over the CAN bus to the different actuators in the car. So you can talk to the brake pedal and say, okay, push the brakes to 30%. Okay, put 2 Newton meters of torque on the steering wheel to the right. And then our software computes, it runs an optimizer to say, okay, if I want the car to be here, this is the actuator commands that I should make in order for the car to end up here in 2 seconds.
That CAN bus, that is, as I understand, the software brain, or I guess the interface to software components that control the mechanical outcome of those software signals to the car. Can you talk more about the CAN bus and how much accessibility that interface gives you to control over the car?
Sure. So you can think about CAN kind of like Ethernet. It's a little bit different, but the same way Ethernet can connect multiple computers together, CAN connects multiple car ECUs together. Now it's an actual bus. Ethernet's not a bus. You need a hub or a switch or something. But basically, like the steering ECU is connected to the engine ECU, is connected to the brake ECU, is connected to the ECU that controls the power windows. They're all connected on this bus, and they can communicate with each other. So what our software does is basically, they're usually the cars that we work on already have these features, but they have low quality versions of these features. So what you do is you unplug the module in the car, the driver assistance module in the car. You plug our thing in instead, and then instead of it saying how to turn the steering wheel, we say, okay, turn the steering wheel this much. It varies immensely from car to car, but a lot of cars have these basically CAN commands that you can send that say things like, torque the steering wheel, or step on the brakes, or set my cruise speed to 55.
When you're interfacing with them, is it a frustrating interface? Do you have to build like a shim over the interface to make it more palatable to deal with? Or is it, do you look at it and you're like, this is actually a reasonably well-defined piece of software?
Yeah, so it is reasonably well defined because it's small. Whenever I've found software engineers are forced to like go to bottlenecks. So the interesting thing about CAN is, so Ethernet has like an MTU, has a packet size of like 1500 bytes. CAN has a packet size of 8 bytes. So you really have to cram all the information in there. Now, the protocol is different from car to car. We have this open source project called OpenDBC, which is basically a DBC file. It's a specification that documents what each signal on the CAN bus means. And we reverse engineered them for a lot of the cars, so you know like how to look up the correct signal to send. We put a shim on top of it. We put maybe it's like a hardware abstraction layer for cars. We call it interface, and then every car can be commanded at least through the same kind of interface.
Is there a lot of variability in the underlying CAN bus technology? Do you have to write a lot of like connectors between your interface and the CAN bus interfaces?
So the CAN bus itself is standard in the same way Ethernet's standard at the hardware layer and at the like framing layer. But once you get into the protocol layer, it's completely different from manufacturer to manufacturer. So we wrote, maybe the shims are like 500 lines of Python for each car. And people have now, there's been a few people in our community who've written ports. They've written ports for the Chevy Volt, the Autopilot Tesla, the Hyundai. It's 500 lines of Python. So.
The Casper mattress was designed by an in-house team of engineers that spent thousands of hours developing the mattress. And as a software engineer, you know what kind of development and dedication it takes to build a great product. The result is an exceptional product when you put in the amount of work and effort that went into the Casper mattress. You get something that you'd use and recommend to your friends. And you deserve an exceptional night's rest yourself so that you can continue building great software. Casper combines supportive memory foams for a sleep surface that's got just the right sink and just the right bounce. Plus, its breathable design sleeps cool to help you regulate your temperature through the night. Stay cool, people. Stay cool. And buying a Casper mattress is completely risk-free. Casper offers free delivery and free returns with a 100-night home trial. If you don't love it, they'll pick it up and give you a full refund. Like many of the software services that we have covered on Software Engineering Daily, they are great with refunds. Casper understands the importance of truly sleeping on a mattress before you commit, especially considering that you're going to spend a third of your life on that mattress. Amazon and Google reviews consistently rank Casper as a favorite mattress, so try it out. Get a good night's rest and upvote it yourself today. As a special offer to Software Engineering Daily listeners, get $50 towards select mattress purchases by visiting casper.com/SEDaily and using the code SEDaily at checkout. Terms and conditions do apply. You'll get these select mattress purchases if you go to casper.com/SEDaily and enter the code SEDaily at checkout. Thank you, Casper. Tell me more about the people in this community. What kind of people are these? Are they software engineers, or are they hackers that decide to learn how to become software engineers? And what characterizes somebody who gets into the open source car community?
You'd have to ask them. I don't really know. The way I think about community building is, I don't care why you're here. As long as you're here, as long as you want to help, that's cool. I'm not gonna like look into your background or anything. I'm not gonna ask you who you are, what your gender is. I don't care. Just show up and hack on cars. So I don't know. You'd have to ask them. Slack.comma.ai.
Okay, maybe I will. So this CAN bus interface, is that basically a solved problem, and you've kind of solved the interface between commands that you can issue to the car and that car using those commands, and you're pretty much operating at a higher level of abstraction where you're sort of thinking more about the user interface and the machine learning models?
Yeah, recently we've gotten, at least in some of the cars we have, like our Honda Civic model is now very good. So the Honda Civic goes where we tell the Honda Civic to go. So yeah, I mean, that's kind of the controls part of the self-driving car. And then, yeah, so our level of abstraction above the like car-specific actuators is how much gas do you want, how much brake do you want, how much steering do you want? What angle do you want the steering wheel to go to? And then the level of abstraction on top of that is here's a trajectory in car space that we want you to follow, right? So like, here's the line that we want the car to go, and here's how fast you should be going at each point in that line. I mean, there's a level of abstraction above that, which is here's the path we want the car to follow. And the distinction between a path and a trajectory is the trajectory must start with you. The path might not, right? The path might be 3 feet to your left. So then we use an optimizer to figure out how to bring the car onto the path. So from a path, we generate a trajectory. Now, the paths are what's outputted by our machine learning model.
Okay, so path is the ideal scenario. Trajectory is, in reality, we are at this point in space and we need to gravitate closer to the path.
Mm-hmm. You can think of path as like the GPS track. If you drove like one GPS track and you want the car to go exactly on the same track again.
Mm-hmm. And then the trajectory gets translated into actual commands for like gas and twitching the steering wheel and so on.
Yeah, so after the trajectory, we have the lower level interface, which goes in and says, okay, well, the trajectory says your steering angle should be 4 degrees right now. It's currently at 3. So apply some rightward torque to the steering wheel to get it to move to 4.
Okay, and so before we get into the path level and the machine learning stuff, can you tell me a bit about translating the path versus the, I guess, like taking the path and saying we are at this point in space and we need to adjust our trajectory. Tell me about how that translation layer, that diffing algorithm works.
Sure. So we use an optimizer. I think it's linear in it's model predictive control. So basically you have costs, and for example, one cost is jerking the steering wheel. You never want to jerk the steering wheel too much. This is a comfort thing. There's a safety thing way further down the line as well to make sure you never jerk the steering wheel. But so we say, okay, given that we don't want to move the steering wheel faster than this, or that we want to minimize like jerk when we're using the brakes, output the idealized actuators. And then we even started to go a little bit further, which is forget the idealized actuator. What is the actual actuator model of the car, right? So you might tell the steering wheel to put 3 Newton meters of torque to the right, but it might not listen to you. It might only put 2, or it might put 3 Newton meters 100 milliseconds late, and you have to model all of that. And the more accurate your model is, the more you can drive the car without feedback. Now, it's a closed loop controller, so it does eventually use feedback, which is, okay, I told you to go to 4, you're only at 3.8. Okay, the error is 0.2. Put that into the optimizer next time and output that.
And the trajectory configurator, or whatever you call this thing, whatever reforms the trajectory and aligns it with the path, do you have to make car specific things? Because it's, if I guess you have different costs that relate to the Civic versus the Accord.
Yeah, so we have a bunch of numbers that vary from car to car. I'm not really the expert on this stuff here, but we have things like the actuator delays, which vary from car to car. For example, the Civic takes about 150 milliseconds to respond to a steering command. The Prius takes like 350. So, you have to basically decide how early do I want to start steering based on my lag.
How did you discover those benchmarks? Did you just have to do a bunch of testing?
So we're at the point now where we can just build models from the data. So we have a lot of historical data about, what it told the car to do and then what the car actually did. We're getting all this data back from our users. And then once you have that, you're like, okay, let's figure out what model we want to fit to that. And we are using all classical models for the vehicle dynamics. I mean, you could go full neural network. You could just try to have an RNN predict it. But yeah, we stick with the classical stuff there.
Yeah, I mean, if that's working, I mean, this is something you would probably find out pretty quickly if you tried to do that and like, oh, well, the car's not responding as expected.
Well, you can always do better. You can always, your model can always be more accurate, right? In theory, if you had a perfect model, you wouldn't need a closed loop controller at all. You would just be able to just tell the car where to go and it would go there. Now, of course, drift and error actually accumulates in the real world. So, you close the loop. Now, how quickly does error accumulate? Well, if your model's really bad, it might accumulate in 100 milliseconds. If your model is good, it might take 10 seconds.
Okay, so I think we've kind of covered how, well, actually, I want to go a little bit more into this. So you've got the car at any given point in a drive has some, I guess, miles per hour it's going and other, like there's state of the car, and then it's position in space, and then you have the path, which is, I guess, the ideal. What are the variables in a path? Does a path include like the ideal velocity that a car would be driving at once it was on a path in a given place? And I guess how rapid is the cycle of checking between the car's point in space and tweaking the trajectory so that it's closer to the path?
Sure. So our outer planning loop runs at 20 hertz, so it's done 20 times per second. That goes all the way down from the vision to the new trajectory. And then the low-level controls, which actually turn the trajectory into actuator commands, run at 100 hertz.
And can you tell me more about like the variables of a state and a state transition and how a state transition proceeds?
So this is all, it's in the Autopilot, it's in serial log cap PNP. These are all the messages that go back and forth between the different processes on the thing. So the path is, you can think about it just in XY coordinates with the car at the origin and facing forward. So this is called car frame. At this point, our car is reasoning in 2 dimensions, not 3. And, where the path actually is, you can imagine a big, kind of a Cartesian grid, and here's the path drawn out. As far as trajectories go, so in the path, we don't know how fast we should be going, but we do know where the other cars are. We know where there are obstacles, and we know where your lead car is. So the optimizer, the same optimizer that turns XY paths into trajectories, also figures out, given that there's a car in front of me moving at this speed, how fast should I be going at each point? And then the low-level controls turn that into, okay, this is how much brake you need to apply to be going that fast at this point. And of course, you put like costs on deceleration, acceleration, and definitely costs on jerk.
Okay, and much like the lower-level CAN bus interface layer, it sounds like this sort of adjustment between the trajectory and the path is maybe not solved, could always get better, but you're in pretty good shape, and you don't spend much time thinking about this?
Oh yeah, once you know the path and like where the object is that you want to stop in time for, that's a complete state. I mean, it's not going to be like a state problem really beyond that. Controls is largely a solved problem. So what our controls engineers here are doing a lot of the time is adding new cars and making the new car models as good as the old cars.
Okay. And is there a lot of demand for that? I mean, do you have people that are like, oh, I'm ready to join as soon as you get my Ford Pinto interfaced? Oh
yeah, when we had cars, we see we're getting into the lower hanging fruit now, but when we added Toyota was huge just because they're so popular.
Fascinating. So let's go higher level. So it sounds like, I guess, what do you spend your time thinking about in the company? Like, I mean, should we just skip to the path area where you're, working on the machine learning models? Is that your area of focus, or are you? Because it sounds like there are some different teams, and there's not just a singular focus. You've got some different areas of the project that are being worked on.
Yeah, so I spend a lot of my time. I mean, we're a 15-person company now, so I do spend a lot of time managing. But as far as the technical problems that I work on, maps have been consuming a lot of my time lately. So we want to open source HD maps of all the highways in America by the end of the year. And the thing is, the companies that have done this before us, because there are data sets you can buy now from like Usher Maps or TomTom that already have this, but those companies spent millions of dollars to create those maps. Those companies literally outfitted fleets of cars with LiDARs and super expensive GPS systems. We want to use our existing fleet that's already on the road and just make maps by processing that data in really good ways.
Do you have enough coverage of, did you say the world or the United States?
We want to do the highways, the interstates in the United States. Yes, we have enough coverage of them.
Oh, okay.
There aren't that many interstates. There's only like 40,000 miles of interstate.
Got it. So, and when you say high definition maps, you mean if you've had, like, how many cars driving over an interstate do you need to generate a high definition map?
About 5.
So you just need 5 iterations for each interstate.
Yeah, if we have 5 paths, and they can't all be in the same lane, they have to be kind of spread out a bit. And yeah, and then we can get everything we need pretty much.
Why'd you set that goal?
Well, so part of the coolness of maps is we get to figure out where all our cars precisely are. We're improving our localizer, which is pretty much all like Waymo and stuff need the LiDAR for. They really only need the LiDAR to figure out where they are. People think that the LiDAR is more about, seeing objects in front of you. You can do that really well now with computer vision. What you can't do that well yet with computer vision is localize yourself to 10 centimeters of accuracy. And that's what we're working on building. So the infrastructure that we're using to build maps has many other purposes in the company besides just making maps. And the maps are a cool thing that we can give away for free, and hopefully... How much have VCs invested in maps? I would love to see their investments go to zero.
So finding your point in space, is that like if I'm at some point in space driving on an interstate and I've got a camera facing forward on my car, you should be able to like hash that image of the interstate or like the combination of that image in the interstate and maybe your GPS or something to a known point in space in mapping space? Or like help me understand what you're talking about when you're trying to improve this accuracy.
Yeah, so it's a big Kalman filter. It's a big extended Kalman filter that fuses together everything we currently know about the car into like a couple of state variables. Some of these state variables are like the position, the velocity, the orientation, those kind of things.
What's a Kalman filter?
So a Kalman filter is a way of combining multiple sensors together to get one estimate of a state. So for example, we have a gyroscope inside of the phone, and the gyroscope will measure your rotation in 3 dimensions. Your roll, your pitch, and your yaw. So it's degrees per second, right? But gyros have this interesting property where they have called gyro bias. So occasionally, depending on the temperature of the gyro, depending on a few other things, the 0 is not 0. So when the gyro says 0, it's lying to you and it's actually rotating a little, or it says it's rotating a little when it's actually not rotating. Now, it's very easy to correct for gyro bias by using vision, because if you have a camera looking forward, when a camera's not rotating, it's really easy to tell. Cameras don't have the same kind of bias. So if you want to get a true estimate of the rotation of the car, maybe you combine the camera, which is very good at removing the bias, with the gyro, which is very good at measuring changes in that degrees per second. Gyros are very high frequency, relatively low noise. You combine them and you get one estimate. So that's like what a Kalman filter does.
Cool. Okay, so continue on how what you're doing to improve the accuracy of known where the car is in space.
So we then put everything into the Kalman filter. So you can take your camera, you can take your inertial sensors, your gyro and your accelerometer. We have a raw GPS processor. So a lot of times people think of a GPS as just something that outputs like a latitude, a longitude, and a height. If you've already gotten to the latitude, longitude, and height, the location is already way too garbage for us to use it. That's usually accurate to about like 10 meters. So what we get from our GPS, and we've shipped for sale on shop.comma.ai a high-precision GPS called the Gray Panda, and it tells us not just where it is, but it tells us where each satellite is, and it tells us the measured distance to that satellite. Okay, it doesn't exactly tell you the measured distance, it tells you something called the pseudo-range, because you don't have a shared time clock between you and the satellite. But the pseudo-range is the distance to the satellite plus some constant, and that constant is the same for all like 10 satellites you currently see. So you now have 10 equations. You have 10 linear equations to solve for your position based on the GPS. So we put all of these equations into one big solver and get a really good estimate of where the car is.
And then that GPS estimate coupled with things like what's going on in the camera that's front-facing in front of the car and all that information that's pulled in there. Between those different variables, you can triangulate where the car is in mapping space.
Yeah. So we can dead reckon extremely well, which is dead reckon is you know where you are, give or take some small offset. Then the reason we need like 5 coverage is because we can combine the 5 together. We can take all those sensors from all those times. And it's really cool. You don't want the 5 to all be at the same time. If you have different times, the satellites are in different locations. It just gives you even more equations to solve jointly for the whole position and the whole map. And this is the kind of stuff that nobody else has built yet. No one even knows we have this stuff. This is the first time I'm talking about it.
How are you sure that other people don't know about that?
I'm not saying they don't know about it. I'm saying that I don't think anybody else has really built it. Because, it's not because nobody else can. It's just because most of the other people in self-driving don't see cost as an issue. They like, I don't care if the car costs $500,000. Each one of those Waymo cars costs $500,000. I'm like, well, but I don't think that works. Uber drivers are cheaper than you think. I know you live in the Bay Area and think everyone gets 100K salaries, but they don't. Okay,
so you said that you have with this, you Kalman filter some stuff and you figure out where the car is in mapping space to some degree of accuracy. How much margin of error do you have on that accuracy?
So when we release our maps, we want everything, so the HD maps contain like every lane line, basically. The location of every lane line, and we're trying to get below 10 centimeters. So maybe something like the mean squared error is going to be 10.
Okay. And once you get, let's say you hit your goal of getting this mapping data by the end of the year, how can you leverage that work? What can you bootstrap that to next? I guess you get to bootstrap it to what you're talking about, the highly accurate state space description.
Yeah. So, you can do really cool things once you have this map. So the simplest thing we can do with it is every car right now has a model, and the model says, I think this should be the path. If we can also localize the cars in a map, the map says, well, I think this should be the path. And then we can do intelligent things like fuse the two paths together. We can say, okay, well, that's the uncertainty there, that's the uncertainty there, and we can make the car drive even more precisely. We can also put things like red lights and stop signs in the map very easily. So people think, oh, well, detecting red lights, that's a very easy problem. I can download an app on the App Store that can do that. And yes, you can. You can even get that to be really, really accurate too. The problem, though, is figuring out where you should stop. Yes, I understand that there's a red light in the image. Okay, does it apply to you? Where do you stop? And that's the kind of stuff that you can very easily put in a map. And how do you build that map? Well, where did people stop when they saw the red light? You don't even need to label it, right? You just, where did people stop? I detect the light. I see people stop there. I've seen 30 people stop at that light. They all stopped in pretty much the same place. Okay, add that to the map.
Yeah, and what other, I mean, so red lights and stop signs, that's a very discrete example. I imagine there's other subtleties like, oh, there's a blind turn here, for example, and we want to be able to train our models so that, when you're approaching a blind turn, slow down, right? Like, how generalized can you make that sort of, because it sounds like what you're talking about is, okay, you can have in your mapping data discrete examples of a stop sign, but maybe in certain places in Utah, you want to stop 10 feet behind the stop sign instead of 5 feet behind the stop sign because in Utah, I don't know, the sun is in a certain angle or something. And I'm just saying the more general cases, like you have circumstances in driving where it's hard to discreetly, rule-based wise articulate how you should be driving. But, this is enough of a blind turn that you want to be slowing down for it. And how do you model that?
I don't need to model it. I have big data, right? I've seen 20 people go around that turn before. Here was the average speed. Okay, go that speed.
Average speed. So I guess average speed and direction and path. I guess path just encapsulates how people should be behaving.
It's even more magical than this, too. This is the real magic of Comma.ai I probably shouldn't talk about. But you realize that, let's even say we get that map, and the map is only 95% accurate. Well, that's not going to really be accurate enough to drive a car, but it's accurate enough to train a machine learning model to drive a car. Your machine learning data sets don't need to be 100% accurate.
Can you talk in more detail? What do you mean?
Let's say I added some random noise to MNIST, right? Let's say I messed with 5% of the labels in MNIST. You know MNIST?
Sure, yeah. The hand-drawn things.
Hand-drawn. So I put in like 5% of noisy data, right? When I train my model, it's going to do better than 95% accuracy on the test set.
Citus data can scale your Postgres database horizontally. For many of you, your Postgres database is the heart of your application. You chose Postgres because you trust it. After all, Postgres is battle-tested, trustworthy database software. But are you spending more and more time dealing with scalability issues? Citus distributes your data and your queries across multiple nodes. Are your queries getting slow? Citus can parallelize your SQL queries across multiple nodes, dramatically speeding them up and giving you much lower latency. Are you worried about hitting the limits of single-node Postgres and not being able to grow your app? Or having to spend your time on database infrastructure instead of creating new features for your application? Available as open source, as a database as a service, and as enterprise software, Citus makes it simple to shard Postgres. Go to citusdata.com/sedaily to learn more about how Citus transforms Postgres into a distributed database. That's citusdata.com/sedaily, citusdata.com/sedaily. Get back the time that you're spending on database operations. Companies like Algolia, Prosperworks, and Cisco are all using Citus, so they no longer have to worry about scaling their database. Try it yourself at citusdata.com/sedaily. That's citusdata.com/sedaily. Thank you to Citus Data for being a sponsor of Software Engineering Daily. So I get it. You get a really, reasonable resolution set of data and you build paths based off of that. And then you have the trajectory of the car and you've got the trajectory to path, state machine calibration. And I think that outlines kind of some of your trajectory as a company. So I guess we can talk a little bit more about like the machine learning tactics or the problems that you're encountering or the problems that you're focused on at the machine learning level when you're trying to build these paths. Can you just talk a little bit about that?
So the truth about machine learning is only people think, oh, machine learning is like playing with nets and like, tweaking your activation functions and changing the number of layers. That stuff is all what researchers do. We don't really do research because we don't have to, right? The problem is not that the nets aren't good enough. The problem is what's the data set that you're training on. So in reality, a lot of machine learning problems in industry are infrastructural problems. Karpathy goes into this a bit, where he's like, well, look, here's the 5% of the system that's actually the net. Here's the 95% of the system that's all about cleaning up data and getting it labeled and putting it in the right way and throwing out bad data and validating the net at the end, right? And then running it in production. So yeah, that's what a lot of the challenges are. I could talk about some fancy, our GANs are unstable, but we don't use GANs. It's all supervised learning.
That's such a relief to hear because I have this this deep learning textbook that's been sitting on my table for like a year and a half now, and I'm stuck at like the matrix algebra part. But luckily, I've been interviewing people about infrastructure for a while, so I can, I think I have a reasonable understanding of that stuff.
Oh yeah, deep learning, it's all an infrastructure problem.
Interesting. So tell me more about that. Like, where do you hold the data? So in terms of the infrastructure problem, I guess I've heard these stories about how the self-driving cars or the quote self-driving cars are like driving around collecting data, and then they take the disks out of the trunk of the car and like load the disks into a data center or something like that.
So this is how Street View did it for the longest time. All of Google Street View was hard drives and FedEx. Your latency might be very high, but your bandwidth is very good. Your bandwidth is actually insanely good. FedEx is bandwidth, But no, we don't do that. We use the internet. We compress.
Okay, so the car's driving around. Are you compressing it on the fly? Or are you like every hour you're taking a snapshot and or sending it over when you have Wi-Fi or something? Like, tell me more about the data collection and ingress process.
Sure. So it's HVAC. We're not like the compression is just a normal video codec. Nice one. HVAC's pretty nice. And then it saves them all to the disk. And then it's a toggle if you want to. They have a cellular radio in them too. So if you have unlimited data, you can upload over cellular. If you don't, you can turn that off, and then it'll upload when you get home over Wi-Fi.
It's raw video. That's the data that you're capturing.
It's 5 megabits. So you can, it's less than a HD video on Netflix.
Okay. So the cars are driving around. Yeah, I know you went over this hardware already. I think, what is there, 3 different hardware pieces? You've got the camera at the front of the car, you've got the CAN bus interface thing, and then you've got like a user interface component. Are those the 3 pieces?
The user interface and the camera are the same. So the 3 pieces are the user interface camera. It's a phone. It's a fancy phone. It's got a nice cooling system and stuff. And, you can buy the phone and try to run it on it, but it won't work very well because it won't be kept cool and your USB is going to be flaky. We have like a little USB conditioner board. So that's the main interface piece. And then, we have the CAN. That's the main camera user interface piece. Then we have the CAN interface. Then we have one more thing called the giraffe. The giraffe is basically just a wire, but it's a nice wire, and it lets you flip between the stock system and OpenPilot. So you can toggle which one you want.
Oh, okay, cool.
But it's a wire. So it's a wire, and like think about like you have like a laptop. Here, I plug my laptop into the internet to talk on the podcast, the Ethernet. So I have my MacBook, I have my little USB Ethernet dongle, and then I have the Ethernet wire. So same 3 parts.
And by the way, altogether, those 3 things are what, $1,000? Is that what the cost is?
A little under, yeah.
Cool. Okay, so back to the infrastructure issues. Okay, so you can collect the videos pretty easily. You said some get lost in the ether. I don't know what causes that.
People delete them, people uploads fail, people reformat their reformat their Eon. Uploads don't fail, it retries nicely, but...
Sure, okay, so video hits your infrastructure. What do you do with it?
So we have a big pipeline. It's a standard data processing pipeline. So in the efforts of driving down disengagements, last month we launched this thing, Comma.ai, and it lets you explore all of your drives. It lets you look through like basically a timeline of when your car was driving, and it lights up green when the system was engaged, blue when you were driving, and then red or orange when you were taking control. And then what we're asking the users to do is label the reason that they took control at each place.
And do you send them like emails and ask them to do it, or are people just, I guess these are pretty engaged like hacker people, so they're probably perfectly willing to do this kind of stuff.
These are very enthusiastic people, and it's for now it's less of a we're using this for the machine learning and more of a we're just you label your data, you show me where your car's disengaging. If you're one of the people who's enthusiastic enough to label, guess who I'm going to prioritize making the car better for?
Yeah, okay, interesting. So again, disengagements are when the person intercedes, like you're basically assuming the person that's driving the car is keeping track of what the quote self-driving car. I know you don't like that term, but whatever. The autonomous. You probably don't like that term either. The autopilot engaged, or the what's the term?
What the computer is doing.
The lane assistant.
What the computerized driving agent.
Yes. The driving agent. So the user is watching what the driving agent is doing, and occasionally the user is saying, this is not right, and grabs the steering wheel or presses the gas. And so that is going to get labeled. That point in time where the user interceded is going to get labeled, and then the video hits your end, and then you can flag those video frames and then present them to the user and say, hey, what made you do this?
Yeah, that's pretty much what it is. I mean, most disengagements are not like safety related. Most disengagements are just like, oh, I wanted to get off that exit, or I wanted to go faster, or,
And those ones you can just ignore?
Well, no. I mean, they're interesting data points. We didn't do what the user wanted us to do.
Fair enough, yeah.
So, we have to make it better.
Yeah, and then so do you have a schema for the labels that people can say? Like, can they say, I was going to hit a car here?
Yeah.
Like that's.
So we have a basic set of labels, and then we have another, and you can fill in a box. But the labels are pretty good. This is something we're going to really push on starting next year. Like right now, the car will just continue in a straight line. But maybe next year we start thinking about, okay, let's actually start taking exits. Let's figure out what the user's intent is. Where does the user want to go? What's the desire? And yeah, that's something that becomes easier to think about when you have maps.
Right. Okay. So right now the car just stays in a straight line. So it only works in circumstances where you're going in a straight line, where you're not making turns?
No, that's not true. The car will work all the time, but if you have choices, right? So say you're in the right lane on a highway. You have a choice. You could continue straight on the highway, or you could get off the exit. If the system's left alone, it will always take whatever the more common choice is.
Oh, okay, I see. So I should know this. So when you get in the car, you enter some destination, and the car... No, you don't. Okay.
You don't enter any destination. When you come to a fork in the road, it'll do whichever one looks like the obvious continuation of the road.
Okay.
And if neither of them do, it'll just pick randomly.
Okay, so I understand. How does the car know where I'm going if I don't put in a destination?
It doesn't. Think about you driving, right? If you drive maybe 40 minutes. Think about you as the passenger in a car, and the driver has no idea where they're going. How often do you have to tell the driver anything?
Let's see. How often do I have to tell the driver anything? I guess not very often.
Exactly. So think about it like that, right? Like every time you would have to tell that driver something, you have to take control of the car. But most of the time, the driver just keep going straight. Just keep going straight. No, keep going.
So is that to say that, like, I take my trip to the office every day and the car learns how to drive from my trips to the office?
I mean, it learns to drive from all the data. It learns it not learns to drive. This is an interesting distinction. It learns the definition of driving, and it learns the definition of driving from everybody. It doesn't like learn to drive from your drive. This is a very layman's understanding of like this kind of stuff, right? Like, to say that a ImageNet classifier learns to recognize chairs. Recognize, that's so anthropomorphized. Ugh. Don't you actually mean learns to like
probabilistically estimate?
Yeah. Or even just learns the definition of chair, right? Like that's more what it's doing.
Okay. Definition of chair according to some like set of polygons or colors from an image.
According to who knows what. According to here's a million examples of chairs and here's a million examples of not chairs. What do those ones have in common that those ones don't? Okay, that's a chair.
Right. Okay. Not to get lost in this like semantic discussion, but so when I get in the car on the first time I plug in my Comma.ai Prius, it's just going to take me on the road traveled by the most cars that have recorded.
It's not going to take you anywhere. So it's a lot more like a cruise control system, right? Like you get the car up to speed. You're like, okay, now I want to go. Okay, engage. And it will continue driving for you.
Okay.
Which is, the truth is, that's most of the time what you want, right? Like, how annoying is it if you had to put in your destination in a nav system every time you wanted to drive to work? And the thing talk to you every time? I know I have to make that left. Yeah, I make it every day, right? So, you do the parts that are something and let it do kind of all the unconscious parts.
Yeah, and I mean, at the same time, it's like, you're on your 25-minute commute to work, and some days you're tired, and some days you might be more liable to slam into a car in front of you, and I'm guessing that a lot of this, the appeal here for in this stage of things is the car may help you from, slamming into the car in front of you.
No, not so much today. I don't know. I mean, it might, but I don't sell safety, right? You're trying to sell safety. Don't sell safety. Build safe things, but don't sell safety. It's like cruise control, right? It's just nice. Like, the worst part, driving in traffic. Driving in traffic's just terrible. It's just like, I have to like do this. This hurts, right? Versus, you turn the system on and then you just watch. Think of the difference between being a passenger in traffic and being a driver in traffic.
Well, a passenger in traffic, I'm staring down at my phone.
Well, don't do that. Actually, you can't do that anymore. We have driver monitoring now. We're watching the drivers.
Okay. I mean, honestly speaking, in that circumstance, I'm not sure what I get, because I guess I could listen to music without moving my foot on the pedal, or I can focus on my podcast a little bit more.
Do you use cruise control?
There was a period of time where I was driving from Bellevue to Seattle to work at Amazon, and I did not use cruise control under that circumstance. The only circumstance I used cruise control in the past is like when I was like driving to San Antonio from Austin, which is like an hour and a half drive.
Sure. Well, why don't you use cruise control?
I'm a little scared of it, honestly. Like, I'm afraid that if I put on cruise control, I don't know. Like, I'm incentivizing myself to give more control away, and I'm a little afraid of that. But I mean, maybe I'm an anomaly there.
I mean, so you can think about it like that. You can also think about it as you can now focus on other parts of the driving task, right? The driving task has a lot of parts. The driving task has, I don't know. I mean, I don't try to sell these things at all. Don't buy one. I'm not trying to make any kind of, everything Comma.ai sells is completely useless.
Well, it's a bootstrap.
No, it's not a bootstrap. It's just useless.
Useless, okay.
Yeah, useless. But it's so good. I mean, like, winning self-driving cars will be so much fun.
Yeah, I mean, okay, I want to talk a little bit more about this data pipeline, because we've got like 10 minutes left, and I want to talk a little bit more about that, and then we can zoom out a bit. But this data pipeline, okay, so what is interesting about it? So it's you're processing video, you're doing machine learning on video. Just, I don't know, give me the abbreviated description of what's interesting and what's hard about it.
I think we're now at like, it's like 0.5% of a YouTube with the video we get. So, it's a huge amount of video being uploaded constantly. Just categorizing it, putting it all in its right place. It's just a data pipeline. You gotta, okay, what if you have out of memory? Well, you gotta retry. What if you're getting an error? Well, and maybe you don't retry. Maybe you flag those as errors on this stage. And it's like a multi-stage pipeline. So first we extract like a bunch of basic stuff from the data, put it into this new canonical format, and then we can do things like, okay, add it to our internal map, pre-process it for the user's Explorer thing. Maybe we're gonna add a stage pretty soon that takes guesses for all the reasons for the disengagement, right? The users shouldn't have to label everything from scratch. They can just refine the labels that our machine learning system outputs, right? So you got to run that machine learning in production, and you got to deploy that, and you got to install that.
What framework are you using, and what cloud provider are you using?
We're using Azure, and as far as a framework for the tasks, we've written it. There isn't really like a good one, except maybe for Google Cloud Dataflow, but that one's only on Google Cloud. Azure gave us a lot of free money, so we love Azure.
Nice. Google Cloud Dataflow. Oh yeah, so Google Cloud Dataflow, that's like the Spark interface or something like that. What's appealing about that?
Yeah, so it's based on like Apache Beam, but they have the good Python client for it. So everything we do is in Python. I don't want to write any Java, right? I want to use Spark. I use Java. So yeah, we've effectively written something. We're using, I think we have some message like RabbitMQ or one of those message queues. Actually, it might just be Redis now. I think we're really just using like Redis and a bunch of long-running processes, and the thing is pushed onto the Redis queue. And I've also moved off of infrastructure and controls now. I work on mapping and machine learning. But yeah, it's basically like, when something comes in, it adds a event to a Redis queue, and then so now we need, you start up a scheduler process which tracks like that file throughout its lifetime, and then can launch more sub processes and check for failures and check for timeouts and check for all those things.
Cool. Yeah, maybe, if any of your infrastructure engineers are listening, they can feel free to ping me. I'd love to do a show on that. I'm sure that would be an interesting show. Let's zoom out a little bit, because that's what you're doing in your job. I mean, so first of all, the process of zooming out from being the hacker who does the 10-hour Twitch sessions of simultaneous localization and mapping to being a manager, this is more of a general software engineering question, but how have you found that transition? What's been difficult about it for you?
I don't know. I'd rather work with computers and people, but I also like high leverage. So you can view people as just like they're like an IDE. And this is really just reflective on how bad IDEs are, that people are better. No, I don't know. We have very good people here now. We have very good, our bar is extremely high. We fired half the people who've ever worked here. It's hard to get a job here. It's hard to keep a job here. But, the advantage for this is everyone kind of respects their coworkers because they're all very good.
Definitely. So simulations, this is something that I think you do not do, but it's something that Waymo does a ton of. Like I read this, I think, Atlantic article about Waymo's, development and how much simulation they do. Tell me about the pros and cons of simulation.
Well, so you can think about simulation. It's a little bit better. Building a simulator is a little bit better than trying to write a car from the rules. Think about writing a car from the rules is kind of like the computer vision problem, and the simulator problem is kind of like the computer graphics problem, right? So it is computer graphics. That's how these simulators are actually written. Now, part of the problem with using simulators as like a scalable strategy to get to level 4 is, at least if you're hand coding your simulator, you're going to run into the same problem as hand coding the driving system would be. There's going to be all these edge cases that you're going to miss out on. So simulators are good for, Chris Urmston has a quote that I like about simulators: simulation is doomed to succeed. You can always build a system that succeeds in your simulator. Does that mean it works in the real world? Unclear. How good's your simulator?
Okay, so you're just throwing it out entirely?
Well, no. So we have a paper. We have one paper, actually. It's on archive. It's self-published. But it's called Learning a Driving Simulator. And that's when we'll start to use simulators. Once we can learn a simulator from data. Because if you've learned a simulator from data, you've now kind of fixed this edge case problem, right? We don't have to worry about, but learning simulators from data is extremely hard. So I'm waiting for a few more papers to come out. One of the cool things that I really liked that came out in machine learning last year was unsupervised learning of depth nets, which we've now started to do internally. So you can learn just from data to predict the depth of every object, right? No labeling required. And we have a lot of data.
How do you do that? How do you do that with unsupervised learning?
So it uses a technique called structure from motion. I mean, you can effectively think that even though our car only has one camera, it actually has multiple cameras, right? Do you see the multiple cameras? Even though our car only has one camera inside of it, do you see how it could have like two?
As you advance through time, you're observing.
Yes, absolutely. Absolutely. Yeah, very good. Yeah, so you have a picture taken now and a picture taken maybe 10 meters ahead on the road. So now you can use those things and you can triangulate points in the image.
And so you just pre-bake in like physics.
Oh, yes. Yeah, so we pre-bake in the
Physics is your labeled data set.
Sure. We pre-bake in the rules of like multi-view geometry.
That's pretty cool.
Yeah, this has been a cool new trend. If there's very distinct rules that truly do summarize all of this, then yeah, of course, bake them in. That is very short. It's part of your net architecture.
So the Udacity team, aren't they doing an open source self-driving car?
No, there's the other open source self-driving cars. Maybe you're thinking of the Baidu team, Apollo?
Baidu, okay.
Yeah, Baidu's doing one. What I really want to see from Baidu is, the problem is the only system their car runs on costs like $100,000 and has to be bought from this specialty company. I don't think that works. I think that if you want to make an open source self-driving car, you want to make it, something people could buy and run. Imagine Linux only ran on $1,000 Xeon processors. Well, it never would have been adopted. It's got to run on the Hondas and Toyotas, right?
Okay, you've been really generous with your time. Just a couple more high-level questions. I heard this interview that I think Shiraj Raval did with you on YouTube. That guy's pretty hilarious, by the way. I hadn't seen anything of his until I watched your interview with him, and it was pretty funny. But one thing he asked you is about the singularity, and you had a pretty strong opinion on the singularity. Tell me what the singularity means to you and why you think it's inevitable.
When computers can do every task better than humans, and I think it's inevitable because computers are getting smarter and humans aren't.
Okay. And do you have a time horizon, or are there some triggering events in the future that you're looking for indicators that this is going to be happening?
Well, here's kind of what I like to think about. So I have about 100 trillion weights. I have about 100 trillion synaptic weights in my brain. I think we're about 1 million fold off from that. I think some of the biggest neural nets. Well, let's see. So the neural net that we use on our car, actually the tiny one only has 1 million weights. So that's actually off by a factor of 100 million. But you can train big ones now that have about 100 million weights. So you're off by about a factor of 1 million. So 1 million. So that's 2 to the 20. I probably got that wrong. Oh yeah, it's 2 to the 20 because 2 to the 24 is 16 million. So 20 Moore's laws. So 18 months, 30 years.
30 years.
Contrary to popular belief, Moore's law is not over. Intel is over.
Okay.
I can't believe Intel 10 nanometer fiasco. It's short Intel stock today.
That sounds like a good place to stop. George Hotz, it's been really fun talking to you, and I'm a fan of your work. I'm a fan of your thesis, and your attitude makes for some entertaining interviews.
Sounds good.
GoCD is a continuous delivery tool created by ThoughtWorks. It's open source and free to use, and GoCD has all the features you need for continuous delivery. Model your deployment pipelines without installing any plugins. Use the value stream map to visualize your end-to-end workflow. And if you use Kubernetes, GoCD is a natural fit to add continuous delivery to your project. With GoCD running on Kubernetes, you define your build workflow and let GoCD provision and scale your infrastructure on the fly. GoCD agents use Kubernetes to scale as needed. Check out gocd.org/sedaily and learn about how you can get started. GoCD was built with the learnings of the ThoughtWorks engineering team, who have talked about building the product in previous episodes of Software Engineering Daily, and it's great to see the continued progress on GoCD with the new Kubernetes integrations. You can check it out for yourself at gocd.org/sedaily. And thank you so much to ThoughtWorks for being a longtime sponsor of Software Engineering Daily. We're proud to have ThoughtWorks and GoCD as sponsors of the show.
Wow.